So, hello everyone. Thanks for letting me speak on this topic. And so, this is a joint work with Zalan, Molnar, and Alexa. So, the topic is distinguishing colorings and proper colorings without the axiom of choice. So, I should say that the main motivation comes from a 1991 paper due to Fred Galvin and Peter Comiat on the fact that the axiom of choice is equivalent to any graph has a chromatic number. So that's a very amazing result. And recently, last year, there was a new research on distinguishing colorings and axiom of choice, and but there were certain disputes with the paper, and we will focus on that. And the main result, I will discuss everything, but let's first go let's first discuss the basic infinite graph theoretical definitions. So by a graph, we mean a set of vertices and a set of edges. A proper vertex coloring of a graph is with the color set C is a mapping such that any two adjacent vertices V1, V2 get two different colors. And similarly, we can say the proper edge coloring of the graph with the color set C is a mapping over the edges such that any two adjacent edges get two different colors. And now suppose C is a set and cardinality of C is kappa for some cardinal kappa. We say that G is kappa vertex colorable. There exists a proper vertex coloring F from the vertex set to C, and G is kappa proper edge colorable if there is a proper edge coloring. Now, the least cardinal kappa for which G is kappa proper vertex colorable or kappa proper edge colorable is the chromatic number, and analogously chromatic index of G. Okay, now I discuss the definition of axiom of choice and Koning's lemma. So axiom of choice has several equivalents, and the well-known most of the well-known equivalents are well-ordered theorem that any set can be well-ordered as well as Zorn's lemma. But in several graph theoretical proofs, especially infinite graph theoretical proofs, we use axiom of choice as well as we use axiom of choice in disguise of Zorn's lemma, and as well as Koning's lemma for countable situations. But let's discuss the definition. So any infinite family of non-empty sets has a choice function. And we work with Zermelo-Fraenkel set theory without the axiom of choice. Now recall that a graph G is locally finite if each vertex has finite degree, that it has only finitely many neighbors. And G is connected if any two vertices are joined by a path of finite length. Now, Dennis Koning proved that in 1927 that every infinite locally finite connected graph has a ray that is an infinite path with no repeated vertices. Now, it's important to recall that Koning's lemma follows from axiom of choice, but it is strictly weaker because Koning's lemma does not imply axiom of choice. And neither you can prove Koning's lemma in ZF. So there is some part of choice needed to prove Koning's lemma. So that's why we call Koning's lemma as a weak choice form, because Koning's lemma follows from AC. It is not provable in ZF, and there exists a model of ZF plus negation of AC where Koning's lemma holds. The most popular model is the Paul Cohen's model from 1963, which Cohen constructed to prove the independence of the axiom of choice. In that model, Koning's lemma holds actually, but that's of course, that's a model where axiom of choice fails. It was designed in a way. Okay, so before discussing the theorem of Comiat and Galvin, so I would like to discuss the essential two different definition of cardinals in ZFC and in ZF, because these two difference makes a lot of changes. So okay, so let us say two sets X and Y are two sets, and we say that cardinality of Y, we note, this is a notation, like cardinality of Y equals to cardinality of X if there exists a bijection, if there is a bijection F from Y to X, and we can say that X and Y are equipotent. And a set kappa is a cardinal if it is the cardinality of some set X. Now the difference is here. With axiom of choice, we know that any sets are well ordered. So note that if X is a well orderable set, then there exists a ordinal alpha such that X and alpha are equipotent. And now you choose the minimal ordinal as a definition of the cardinal here. So the cardinality of X is the minimal ordinal such that alpha and X are equipotent. But this thing doesn't hold without AC. But because we know that there are non-well-orderable sets without axiom of choice. But then in 1955, Dana Scott invented a new definition with that's popularly called Scott-Stricken set theory, that without axiom of choice, the cardinality of a set is a set Y such that there exists a bijection between Y and X, and Y is of least rank. And the details can be found in the paper of Dana Scott from 1955. Now, again, this concept of Hartogs theorem is very essential in the proof of Calvin-Combes proof. So suppose X and Y are two sets. We say that X is less than equal to Y if there exists an injection F from X to Y, and cardinality of X is strictly less than cardinality of Y if there exists an injection but no bijection. So that's the difference. Now in 1915, Hartogs proved in ZF that there exists a Hartogs number for each set A. What is a Hartogs number? It is the least ordinal alpha such that there is no injection from alpha to A. Now under AC, axiom of choice, any two cardinals are comparable with respect to this ordering. Now thus, if A and B are arbitrary sets, they are well ordered, of course, then either X is less than Y, that is, there exists an injection from X to Y, or there exists an injection from Y to X, or there exists a bijection from Y to X. We just merge it in this situation. So if we take axiom of choice, then A is an arbitrary set which is well orderable. So the Hartogs number is nothing but cardinality of A plus, so the successor cardinal basically. So the Hartogs number will be just alpha A plus. Okay. Now the important result in 1991, Fred Galvin and Peter Punjat used Hartogs theorem, the theorem that this. This is the Hartogs theorem. So they used Hartogs theorem to prove that axiom of choice is equivalent to any graph has a chromatic number. Note that this is very important, that this direction is very trivial. Axiom of choice implies any graph has a chromatic number, because any graph will be based on a well-ordered set of vertices, and then you can easily carry out an argument by some greedy argument. You can easily carry out that any graph based on a well-ordered set of vertices has a chromatic number, and that argument directly grows through transfinite recursion without using any form of axiom of choice. So the direction from 1 to 2 is pretty trivial. But the hard part is from second to 1, 2 to 1. And that's the genius of this result. They used Hartogs theorem and a very interesting trick to prove that any graph has a chromatic number implies that all sets are well orderable. Okay, so the main point is that this 2 to 1 implication is the most the hard implication. Now, I will discuss about distinguishing colorings and a recent result of Stavitsky last year. Okay. In 1977, Laszlo Babai introduced distinguishing vertex coloring under the name of asymmetric colorings, and Kalinowski, Pilsniak, Polish commentators, they introduced distinguishing edge colorings as well. So this is just a definition, an automorphism of a graph, and if F is an assignment of colors to each vertices or edges, then F is a distinguishing coloring if the only automorphism that preserves F is identity. So that's the definition of a distinguishing coloring. Okay, and similarly we can define the kappa distinguishing vertex coloring and kappa distinguishing edge coloring like the proper vertex and edge coloring. as well as the distinguishing number and the distinguishing index. The difference is just the difference between the proper coloring and distinguishing coloring. But the distinguishing number, distinguishing index is similar like chromatic number and chromatic index. Okay. Now, last year in 2023, Marcin-Stawicki proved the following theorem by assuming that the cardinality of color classes are well-ordered cardinals. So that makes the argument very trivial, because when you are working with cardinals which are defined in ZFC, then you are assuming that the cardinals are ordinals as well. But there is a strict difference between cardinals in ZF and cardinals in ZFC. Note that cardinals in ZF can be non-well-orderable set. It can be well-orderable set. But in ZFC, all cardinals has to be ordinal, so they has to be well-ordered sets. So because of this assumption, Stawicki's argument became very trivial actually. And he proved that Koning's lemma implies any infinite, locally finite connected graph has a chromatic number, chromatic index, distinguishing number, distinguishing index. So the argument he used, the interesting part is that he proved the fourth point, that is the distinguishing number, and the fifth point, that is distinguishing index. So any locally finite connected graph has these properties, implies Koning's lemma. That's what he proved. That is a suitable development, but the main problem is that he worked with cardinals which are ordinals. So the hard job became much more trivial. So what we did in this, yes, so we actually figured out a kind of argument which is inspired by a 2006 paper of Horst Herrlich and Eleftherios Taktisis. They are working in ZF actually. And so the name of the paper is on the number of Russell socks, or 2 + 2 + 2 equals what. So this was a paper published in 2006, and there was a very interesting combinatorial argument, but we had to suitably modify that argument a bit, and we kind of figured out that any locally finite connected graph as a distinguishing number implies Koning's lemma. But now in this case, we are working with cardinals in the absence of AC. So we assume that the cardinals can be well-orderable as well as non-well-orderable. So the definition that I just introduced by Dana Scott. Yeah, so I will try to present one of these proofs, because I don't think I will be able to present all the proofs, of course. But let's start by the most trivial direction. So I will try to show that 1 implies 2 to 5. This is the trivial direction. Okay. So for that purpose, we need these facts that Koning's lemma is actually equivalent to the property that the union of any countably infinite family of finite sets is countable. So Koning's lemma is equivalent to this property. So this property I am going to use to prove 1 implies 2 to 5. Okay. So let us assume G as an infinite, locally finite connected graph. You pick randomly a vertex R, and then you define V and R to be the set of all those vertices such that drV equals n, where drV equals to n means there are n edges in the shortest part joining R and V. Now, since V and R is finite by locally finiteness of G, so all the neighbors, the number of neighbors of R are finite, and then the number of neighbors of each neighbor is finite. So since finite union of finite sets is finite, so we can say that V and R is finite. And now, since the graph is connected, we can say that Vg equals union of V and R. So of course, by Koning's lemma, which is equivalent to the fact that the union of countably infinite family of finite sets is countable, we can say that Vg is a countable set. Why? Because all these V and Rs are finite, and this is the countably infinite union of finite sets. And that's why it is countable, because we are assuming Koning's lemma here. Now that's why it is countably infinite, and hence it is well-orderable. And since we know it is possible to see by a transfinite recursion technique without using any form of choice, that any graph based on a well-ordered set of vertices has a chromatic number, chromatic index, distinguishing number, and distinguishing index. You just apply the greedy algorithm, just transfinite recursion algorithm, and it works in ZF properly. There is no problem because we have a well-ordered set of vertices, so there is no issues with choice anywhere. Okay, so this direction is pretty trivial because this is a very well-known trick used in graph theoretical constructions, but the other direction is a little bit hard. So we will only sketch the proof of 2 implies 1. And here we use the fact that Koning's lemma is equivalent to any countably infinite family of non-empty finite sets has a partial choice function. So the partial choice function means that it has an infinite subfamily with a choice function. So I will use this fact that this statement is equivalent to Koning's lemma to prove that 2 implies 1. So first assume, so let's go contrapositive, we prove the contrapositive direction. So we assume that Koning's lemma fails. Now, then there exists a countably infinite set of non-empty finite sets without a partial choice function by this statement, because this and Koning's lemma are equivalent. We show that there exists a locally finite connected graph that has no chromatic number, and that's all. Because if we can prove this, then we can say that 2 implies 1. So that direction I will show how to do that. Okay. So first of all, so we assume that these are countably infinite family of non-empty finite sets. So all these A0, A1, A2, these are finite sets. Now, what we are doing, we pick a countably infinite sequence T, so T0, T1, T2, and so on, which is disjoint from the union of AIs. Now consider the infinite locally finite connected graph as in this diagram. So I take the union of all the vertices, all the AIs, and I take the T, this whole set, and this is our vertex set. So this is the entire vertex set. The edge sets are basically you connect Tn plus 1, and then Tn you connect with all vertex of AI, An. So this is the whole graph that we are going to consider, and the target is to show that this graph doesn't have a chromatic number. Okay, so let's see the sketch. So suppose that F is a C proper vertex coloring of this graph that is a map such that if X and Y are adjacent, then they get 2 different colors. Now you see that this is our graph, and let's say C is the color set, and F union An, this set is a range of union An. Okay, so this is the collection of some vertices, and you just take a function f, and the dotted area is the range. Okay, so first I will prove that MC, if you pick C from this F union An, pick any color C from this set, then I claim that MC equals F inverse C intersection union of AI is finite. Because of course, if you take a color from here, it can, some of these TIs can have the, can be in F inverse C, or some of the vertices in union of AIs can be. But I am only interested in those vertices that are in union of AI. But notice that since I am constructing the graph in a way that all vertex in A0 are connected, all vertex are AI, A1 are connected to each other, all vertex of AIs are connected to each other. So if there is one vertex in F inverse C, then this another vertex will not be able to be, so another vertex can't be in the F inverse C, right? Because this is a complete graph. So there will be only one member from each AI, from AIs, I mean. So that's what I wrote it here. Since for any I in omega, no two vertices of AI can get the same color, but there can be 1 or 0. Okay, so my main point is that MC has to be a finite set, because first of all, you notice that, oh, sorry. First of all, notice that this has to be one element sets from each of these AIs. Okay. The second observation is that if this continues till infinitely many, so if MC is infinite, for instance, then it will create a partial choice function. But that's a problem, because I already assume that AIs has no partial choice function. So since AIs has no partial choice function, MC has to be finite. So that's the point. Now I use the fact that MC is finite to prove that F union AN is an infinite set. Because you can write union of AN as union of MC, where C is coming from this dotted area. And this is finite, since finite union of finite sets is finite, and we obtain a contradiction. So this guarantees that F union of AN has to be an infinite set. Okay. So the next step is to show that if union of AN is a Dedekind finite set. This is another thing. So if you work in ZFC, normally Dedekind finite sets are finite sets. But if the axiom of choice is dropped, then there can be some infinite sets which are Dedekind finite. So what is the definition of a Dedekind finite set? That there is no injection from omega to X. Equivalently, for any proper subset A of X, there exists an injection from A to X. A is a proper subset of X. So these two definitions are equivalent, and if any of these hold, we say that X is Dedekind finite. My target is to show that this set that we are considering, this is not only infinite set, this is also Dedekind finite set. Okay, so assume that you take a countably infinite subset of this set like this, and then okay, so this is a trick that I'm not going to explain too much, because this is very much used in choiceless tricks. So I applied this trick to show that there can be no countably infinite subset of F union AN. So basically we are taking BIs and this minimal element of this. So anyway, so this argument shows that F of union of AN, so this part, this dotted area, is an infinite as well as a Dedekind finite set. Okay. Now we use the fact that this is infinite and Dedekind finite set to show that G1 has no chromatic number. How to do that? Okay, so this is the claim. So first of all, this C is the entire color class, and this is what I'm interested right now, F union of AN. So fix any C0 in F union of AN, and let us say index of MC0 is all those indices for which MC0 gets at least one element. Okay. Now since finite union of finite sets is finite, we know that index of MC0 is finite, and F of AM is also finite, because AM is finite, so F of AM has to be finite. So union of F of AM, where AM is in index of MC0, has to be finite. But by claim B, we know that this dotted area is infinite set. So this dotted area is infinite set, and this box is finite set. So there exists at least one B0 which is outside. Yeah. So what I will do, I will define a coloring G where if Fx is mapped to C0, then I will map Gx to B0. But if Fx is not mapped to C0, then the Gx and Fx are same. So for instance, these vertices maps to C0. What I am doing here, I am mapping these vertices to a different vertex B0, which is totally outside. And all the rest of the the mapping F and G are same. Only I am just changing the where So only I'm changing where it should have gone to C0 to B0. Okay, I will, yeah, 3 minutes I can. So that strategy helps us to actually show that, So that strategy helps us to show that we can define similarly a proper vertex coloring. If so, so the previous strategy helped us to reduce one vertex. Now I will do the same strategy. I will reduce 2 more vertex. Okay. So that say these vertices are C2, C0, and C1, and then I will color T0 with C0, T1 with C1, T2 with C0, T3 with C1, and so on alternatively. In this way, I am getting an entire coloring of the entire vertex VG. And the interesting part is that the range part is FAN minus C2. Now, since we know that F union of AN is a Dedekind finite set, and this is a proper subset of the Dedekind finite set. So the cardinality of this set has to be less than the cardinality of F of union of AN, and that's the main part here. So this is the cardinality which is less than this. So starting from the fact that the entire graph has a cardinality, so entire graph is C colorable. I proved that the entire graph is C1 colorable, where C1 is this number basically, this set basically, where this is strictly smaller than C. So G1 has no chromatic number. Okay. Okay. So similarly, the other proofs were done by a bit modifying the graph. So we modified the previous graph a bit more to prove for distinguishing number, distinguishing index, and chromatic number. So there was another result in 1991's paper of Galvin-Komjat that axiom of choice is equivalent to any graph has a irreducible proper coloring, and this is the definition. That it's a irreducible proper coloring if you take F inverse of C1 union F inverse of C2 is a dependent set. Dependent set means not independent set. Okay, so these two are equivalent, and we proved that Koning's lemma is actually equivalent to the version when we restrict it to infinite locally finite connected graph. And this is not as interesting as the previous proof, but I would say this is also kind of less complicated than the previous idea. The distinguishing idea was even more interesting, but I won't be able to present it today. Okay, this is an open question which I wanted to ask, because Tavisky's paper also says that axiom of choice is equivalent to any graph has a distinguishing number, any graph has a chromatic index, and the third variant. But the problem is he worked with cardinals in ZFC. That's the problem. Now the main question is the entire paper we worked with cardinals in ZF. And Komjat-Galvin's paper's main essence was also that he used Hartog's theorem because the things were actually complicated when you are working with non-well-orderable cardinals. But here, this is the open question that is it true that if we work with cardinals in ZF, can we say that any graph has a chromatic index is equivalent to SC? Because any graph has a chromatic number is equivalent to SC comes from Galvin-Komjat's result. But this part is unknown. Chromatic index, distinguishing number, distinguishing index, especially if you drop K1 and K2, like complete graph on 1 vertices and 2 vertices. Yeah, so that's all I would like to say, and yeah, thank you. And these are the main, actually, this is the main paper, which is the motivation behind the research. Yes, so thank you for your attention.